Hello, and welcome to the Georgia Tech presentation on cyber attacks and signature-based intrusion detection for Modbus-based industrial control systems. My name is Nathan Collis Coelho. I'm a Georgia Tech graduate student. This presentation will be released on February 21, 2021. Here we have some acknowledgements on the paper authors, which are Wei Gao and Thomas H. Morris, both from the Mississippi State University. This paper has been presented at the Journal of Digital Forensics, Security and Law, 2014. It's available at the URL link that I am providing here on the slide. The formal citation for this paper is described below. Let's start with an overview. This paper discusses industrial control systems vulnerabilities, particularly using the Network Communication Protocol Modbus. The problem statement is regarding the risks that these vulnerabilities cause, which are inability to monitor, inability to control, or even a completely system failure. We discuss two different models that are used in this paper, which are a gas pipeline and a storage tank test bed. We will discuss some attacks, such as reconnaissance attacks, response injection, command injection, and denial-of-service attacks. Finally, they have implemented an intrusion detection system, an IDS, as a solution to the vulnerabilities from the ICS, Industrial Control Systems. An introduction. SCADA is the supervisory control and data acquisition. It has a strategic importance as it's used for critical infrastructure. However, forensic systems for SCADA control systems are not common. And we have the Modbus, which is the network communication protocol used in industrial control systems throughout many industries. As we see here, we have on the right side the first feedback control loop, which has a PLC connected to a physical process using sensors and actuators. For safety reasons, it does not require a network connection to control. On the left side, we have the second feedback loop, which includes a human-machine interface, HMI, or Master Terminal Unit, an MTU, and we have the human in the loop. This loop uses physical, network, transport, and application layers. For this research, Modbus was used for the PLC to HMI network communication. The HMI and MTU continually queries the PLC for sensor measurements. And here we will discuss the models that were used. We have the gas pipeline. Here on the screen we see the gas pipeline laboratory testbed that was implemented on this research paper. And here we see the water tank testbed that was implemented as well. The water storage tank models and oil storage tank control systems used to monitor oil inventory and distribute oil to refinery processes. We'll discuss 4 categories of attacks. Reconnaissance attacks. Reconnaissance attacks try to obtain as much information about the cyber-physical system as possible, which can then be used for the response injection attacks, command injection attacks, and denial-of-service attacks. The response injection attacks affect the network traffic from the Modbus server to the client as responses to Modbus queries. Command injection attacks inject false control and configuration commands into a control system. Denial of service attacks attempt to break communication links to prevent remote monitoring or control of a system. The research paper describes 28 different attacks. If all the attacks were to be described in full detail, it would make this presentation become very long. So, I will make sure to share some details for each category listed there. Starting with the Reconnaissance Attacks. The address scan attack is a reconnaissance attack that sends Modbus queries to all the legal Modbus addresses and listens to the response. We also have the function code scan attack, which is another kind of scan attack, which walks through all the legal Modbus. Instead of address on the first one, on this one, it runs through the function code and builds a list of implemented function codes by each connected address. We have the device identification attack. The device identification attack uses two read device identification functions, which is built into the Modbus protocol. It allows the attacker to learn the PLC run status, the vendor name, the product code, the major and the minor revision, as well as the vendor uniform resource locator, the URL, the product name, the model name, and the user application name. Lastly, we have the point scan attack. The point scan attack creates a map of implemented Modbus data block addresses, like coils, discrete inputs, holding registers, and input registers for an identified Modbus device address. After the attacker has obtained information through the reconnaissance attacks, they can more effectively use response injection attacks. If an attacker has not obtained enough information through the reconnaissance attack, on the response injection attacks he will start using a sensor measurement grossly out of bounds attack. As we can see here, the sensor measurement grossly out of bounds attack injects process measurements significantly outside the bounds of alarms set points. This occurs because the attacker does not have enough knowledge of the system environment. If the reconnaissance attack is successful, or if the attacker is an expert in this specific cyber physical system, he can then implement a complex malicious response injection attack. The complex malicious response injection attack appears similar to the normal system behavior because the knowledge of the system being attacked, it makes it very hard to be detected by an operator, for example, because what he sees on the screen is very similar to what is expected to happen with a normal system usage. As we can see here, the CMRI, it's not much different from what really occurs before the attack. It's still inside the boundaries of the minimum and maximum expected level of the measurements. Command injection attacks. As I have shared previously, command injection attacks, they inject false control and configuration commands into a control system. Starting with malicious state's command injection attack. Malicious state command injection attack change the state of the process control system. The altered system mode attack injects a command to switch between a manual and automatic mode. For example, the attacker could make it look like the operator wants to run manually the environment instead of just letting the PLC do the automatic control. We also have the altered actuator state attack. The altered actuator state attack changes a system actuator state. For example, a pump might be turned on or off, or a switch can be opened or closed. If an attacker continually uses this attack, it can become a continually altered actuator state attack. On the continually altered actuator state attack, the attacker keeps changing the state of an actuator in a system. This might be done to attempt to cause physical damage to a system component. Once again, if the pump keeps being turned on and off many times in a row, it can be damaged, which is critical to the system. And lastly, we have denial of service attacks. Denial of service attacks attempts to break the communication links to prevent remote monitoring or control of a system. It requires large volumes of injected packets. One type of attack is the invalid cyclic redundancy code attack. The invalid cyclic redundancy code attack injects large volumes of Modbus packets with incorrect CRC. We also have the Modbus slave traffic jamming attack. The Modbus slave traffic jamming attack is specific to a proprietary wireless communication system. This proprietary wireless radio includes a carrier-sense back-off arbitration scheme, which causes legitimate slaves to wait for a clear line to transmit. As we see here, an attacker caused a DOS attack by not allowing the clear line to be transmitted. So, on this paper, as a solution to all the vulnerabilities discussed previously, the authors have developed an intrusion detection signature rules specific for the Modbus network traffic using SNORT in order to countermeasure the attacks that we have been discussing up to here. Standalone rules are implemented using the SNORT intrusion detection tool, while state-based rules are processed using SNORT preprocessor. I will be discussing details about both standalone and state-based rules on the next two slides. SNORT is an open-source intrusion detection system, which is interesting because now anyone can reproduce the behavior that is described in this research article, using these rules and verifying the results. Here we see the list of the standalone signature rules that have been presented on the paper. Even though the list of the attacks that have been provided on this presentation is limited, the signature rule set that I am showing here has all the standalone signature rules described on the paper. So anyone can implement any of these rules on an SNORT system and simulate the behavior to validate the results presented here. Standalone rules parse a single Modbus packet looking for a match to one specific signature without requiring any knowledge of the other packets that traverse the environment previously. If the signature is present in the parsed packet, then the packet is classified as a match and an alert is issued. The standalone rules are implemented using the SNORT intrusion detection tool, as described on the previous slide. They have provided signature rules, which are described on this table, and these rules can be adjusted to any cyber-physical system, as long as you have an expert on the specific system that you are working at, in order to provide the parameters for tuning the signatures for that specific environment. A system-specific whitelist can be developed, which includes all legal function codes a Modbus server supports. The function code whitelist can include all public Modbus function codes as well as any user-defined function codes. And here we see the state-based rules. As well as on the previous slide, on this slide we see all the state-based signature rules that are displayed on the paper. State-based rules, they require the knowledge from the previous Modbus packets or from another source, such as a process sensor. Basically, they need to know either the protocol state or the state of the industrial control system being monitored. The model of the state of the industrial control system is system-specific and requires expert knowledge to develop. The protocol state structure stores the last received Modbus packet. The historical state for the industrial control system holds the command state and the process state. For example, for the pipeline, the command state includes items such as the on-off state of the pump, while the process state includes measurements related to the process. For the pipeline, the process state includes the last pressure reading and other system measurements. And here we can see the results that they have obtained on the paper. As you can see, the signatures have provided excellent results. The detection rate is above 90% for both the pipeline and the water storage system for most of the attack categories. The false positive ratio is outstanding as well. It's below 1% for all the attack categories. This brings us to some of the conclusions here. Industrial control systems, as we can see, they can benefit greatly from signature intrusion detection systems. We can have a security operational center, for example, reading the alerts provided by the SNORT IDS. The Security Operations Center can call the operation engineers to make sure that the process is running as expected. If any alert occurs, we have over 90% of probability that it is a real alert. This occurs because industrial control systems have a regular communication pattern and a predictable system state and control schemes. This regularity and predictability make them excellent candidates for signature-based intrusion detection systems. So, implementing the rules described in this presentation can lead to a more secure critical infrastructure. And lastly, signature-based IDS rules are easily adjustable. Signature-based IDS rules can be customized for the specific system which they protect. As you see here, they have used a gas pipeline and a water tank, and they have used the same intrusion detection signature system. And lastly, we have the references here. So we have this one, it's the first article, it's the paper that I have used for this presentation. The second, it's the paper that describes the test bed, which has the pictures that I have collected for the water tank as well as the pipeline. And lastly, I have collected some information from the SNORT network intrusion detection and prevention systems. I'd like to thank you for joining me in this presentation, and I hope you have enjoyed and learned something with me. Thank you for your time. Have a great day.